In this video, we want to touch on the idea of span for a more general vector space. We did see the idea of span briefly when we were discussing vector space Rn, but we want to discuss it here with a quick example. The definition here should look familiar. We're saying that if we let v1 through vm be vectors in a general vector space V, then these vectors span that vector space V if each vector in V can be written as a linear combination of this collection of vectors. So we're saying everything in V has to be expressible as some combination of this set to be able to say that this set of vectors spans V. So let's look at this example. Let's assume we have two vectors, u and w, that span a vector space V. Let's show that the vector 2u and the vector u minus w taken together, let's show that that set of vectors also spans V. So the way I would look at this one is to start out by saying what we're really trying to do here. We want to show that any vector V from this vector space can be written as a linear combination of 2u, this vector, and u minus w. So let's just write generally what that is. A linear combination of those two vectors looks like some scalar c1 times 2u plus some scalar c2 times u minus w. So let's start at the beginning here. We know any v in the vector space can be written as a linear combination of u and w. Right? Since they span the vector space, any v in that vector space can be written as a linear combination of u and w. So let's say it this way. Let's say that any vector v in the vector space can be written v equals some scalar a times u plus scalar b times w. Now our whole goal is to see what would these scalars c1 and c2 have to be so that this expression was equivalent to this expression. Well, we'll pull some kind of crafty tricks to try to convert this to something of this form. Let's see if we can do this. First of all, I'm going to write v equals, since I really want a 2u here, let me divide by 2 and also multiply by 2 at the same time. Right away there, I'm introducing something that looks like a 2u instead of the u we started with. And notice all that does is changes the scalar out front. To handle the next part, let me write this b times w is b times w minus, well, let's actually do that a little bit differently. Yeah, let's write this as b times u minus u, that's just the zero vector, doesn't change anything it's attached to, plus w. That might seem strange, but at least I'm incorporating a u and a w of opposite signs like we're eventually going to need here. Maybe we can tease this expression out of this one. Let's see what we get. So I'll rewrite this as a divided by 2 times 2u plus, I'm going to separate this out and write bu minus bw. And you can check that this works. If I look closely here, distributing the negative would make negative bu. Well, we would also have a negative bu from these terms. The positive bu out here is out front, b times u here. And then if we distribute our negative to the negative BW, negative, negative makes positive B times W. So this is a little trick that works, and from here what I can do is, picking up down here, rewrite this the same way. Got a B times U here. Let's just leave that alone for now.Maybe we'll come back to that before the next line, but I'm going to leave that there for now and say next we can actually factor a B out of the BU minus BW. And this is looking good, right? Now we have a U minus W sitting here. That's what we need to express V in vector V in terms of. But now we have a problem over here, right? We have a U, but we don't want to express this in terms of U's. We want to express it in terms of 2 U's like we did over here. Well, let's just pull that same trick on this term and write this as B over 2 times 2U. We'll write this as B over 2 times 2U. All right. And finally, we might notice we have the same vector 2U and 2U here. So I can actually factor this A over 2 plus B over 2. I guess I'd be factoring 2U out to the back of this sum. Let's see what that looks like. I'll factor the 2U out to the back of the sum. And notice this is exactly what we want. Now we have some scalar times 2U, some other scalar times U minus V. We have successfully written this vector V we started with as C1 times 2U plus C2 times U minus W, where those scalars are guaranteed to be A over 2 plus B over 2, and C2 will be negative B. So we know, since we started out with an arbitrary vector V in this vector space, we know we can always pull this off and find a linear combination of 2U and U minus W that equals our original vector. And that is our exercise. The next video we'll see a theorem and hopefully wrap up this section.